Good. Well, I would like to thank all of you brave souls for coming to the chemistry talk. My name is Renee Beaton, and I am a professor of chemistry here at Adams State. And it is my pleasure to introduce Sean Rossillon. He's going to be talking about a project that I've worked with him a little bit on, but mainly he's been working with a postdoc from the CSU SLV Research Center where they're working on potato research. And the postdoc, Diganta Kalita, has been coming to Adams State for about a month now and using some of our instruments, and Sean's been helping him out. Unfortunately, he got here a little bit later than we had anticipated, so this research project is really kind of still in the beginning stages rather than what we had hoped would be almost complete at this point. So Sean is going to talk about what they've been doing, what the plan is for the research project, and where they're going to be going in the future. And so yeah, I will let him introduce the rest of this topic.
So I'm, like Dr. Beaton said, I'm Sean Rossillon, and I've been working with the postdoc, Diganta Kalita, on a project looking at polyphenolic compounds found in potatoes. And what we're looking at is some of these phenolic compounds have been shown to prevent cataracts, and this was originally found in colorful fruits and berries such as strawberries and blueberries. And so we wanted to see what happens, or what if these compounds are found in colorful potatoes. Particularly, what we're looking at is the reds, the yellows, and the purples. And so what I'm doing is I'm going to help with the identification and quantification of what we actually find in the potatoes. And so why are we're doing this because cataracts is the leading cause of blindness in the world. Almost 20% of Americans over the age of 40 are affected significantly by cataracts. Most commonly is cataracts are caused by age, but other factors are genetic components, environmental components, and diseases such as diabetes can also play a factor in the development of cataracts, particularly in low-income populations where they don't necessarily have access to these fruits and berries because they tend to be expensive and hard to ship to these places. Potatoes are much more common, and if we were able to get these potatoes to these populations, it could help significantly reduce the amount of cataracts we see in these populations. And we think that potatoes might be a viable way to do that. And so what I'm doing is chromatography technique, forgive me again. And what this does is it separates mixtures of components. So we have a sample, a liquid sample, that's just filled with all sorts of different compounds. And what we need to do is separate them out so we can know what they are and how much of them there are. And so that's basically what chromatography does. And it uses two phases, which is a mobile phase and a stationary phase. The mobile phase is usually gas or a liquid, and it will pull the sample you're trying to determine through what's called the stationary phase. And this one is either a solid or a liquid. And the sample is going to have some polarity, which means it's going to have a relative charge on one end of the molecule or the other. And the stationary phase is going to hold on to these compounds depending on how polar they are. And so depending on how the affinity of the sample for the stationary phase will actually slow it down more. And so the things that are leads to have the smallest affinity for the stationary phase will move through fastest. And depending on how long they run through the column, we can actually identify and then quantify what's in there. And particularly we're using what's called high-performance liquid chromatography. It's a type of liquid chromatography, so we're using a liquid sample and a liquid solvent. And the solvent gets pumped into the instrument at almost 200, around 200 bar, which is about 200 times that of atmosphere. So it's really high pressures, and it pushes it through a column, which we see here. I'll go over the column in a minute, which is filled with, and then Oh, forgive me. I'm not very good at this. So after it runs through the column, it'll pass through a detector, which I'll also go over in a little bit. And depending on the detector, we're using a diode array detector. We'll get a signal, and the signal is correlated to the concentration and the identity. So going over the column for HPLC, we'll use usually a 5 to 30 centimeter long column that has a diameter between 1 and 5 millimeters. This column is usually packed with silica beads, very small silica beads between 2 and 5 micrometers in diameter. And it's coated in our stationary phase. And because this is why the HPLC runs at such high pressures, because these very small beads require a high pressure, or the solvent would never be able to run through. It would take years. We usually use the guard column is there. It's going to be essentially the same as the column itself, and it's going to be using the same stationary phase. But any particulates and anything in our sample that is strongly absorbed will get caught here. They'll be trapped, so that way it won't get into our column. The columns tend to be pretty delicate, and they're pretty easy to ruin. So that's why the guard column is there. And we use the very small beads because they provide a very high surface area. Several hundred meters per gram of column packing is normal. And so it provides a very large area for the sample to be exposed to, allowing for better separation in a shorter distance. Here's a diagram of the column. And so we have the entrance up top. That's where our sample is going to be injected. And then the guard column below it. The titanium frits, all they do is they distribute our sample evenly over the surface area of the column, so that way it's a nice even plug. We don't have a very concentrated spot in a very dilute areas. It makes better resolution for our peaks and better forgive me again, better resolution and better retention, or well, better peaks. They'll look nice when they come off. After that comes the main column. That's packed with again the silica beads. It'll run through there. It takes anywhere from 5 to 30 minutes, depending on what you're using to run through these columns. And then the porous titanium frit back at the bottom just spreads it back out before it goes to the detector. And we're using a diode array detector. It's a ultraviolet visible spectrum detector. And what it does is it shines a light source that emits in the ultraviolet and visible ranges. And this light source will be bounced off of a diffraction grating, which prisms the light into its various colors. Depending on which angle we set this diffraction grating to, we can actually select specific colors of light, depending on what we're trying to figure out. And that'll pass through a half mirror, as you can see on the diagram here. We have the half mirror, and what that does is it lets in part of the light, and it reflects the other light down to this reference side. This reference side, all that does is any variations in the light source can be taken into account before it hits the detector. And then the light coming off of the diffraction grating will come through. This is where our sample would flow through. And this here would receive our light. And depending on how much light hits this, relative to how much light comes through here, we get a signal. And that signal is what produces our peaks. So what we did is we took potatoes and we mashed them up, and then we separated the solids and the liquids. We took the liquids and we extracted them with butanol, which is an alcohol. We did that 3 times to ensure full quantitative transfer of our polyphenolic compounds into the butane. This is what it looks like here. This is from the red potatoes. The butanol would then evaporated off using our rotovap, and then re-dissolved using methanol and water. And then now that we have our samples from our potato extracts, we can run them through the HPLC. And for our HPLC, we use two solvents. One was the 0.1% formic acid in methanol, and the other one was just straight pure methanol. And those will run through the column at a gradually changing proportions over 25 minutes. It started out with 100% methanol, and over the course of about 20 minutes, ramped up to 90% of the formic acid solution, and then back down to 0% over the next 5 minutes or so for the 25-minute runs. And we would see how our compounds were retained. And for analysis, at the time being, we're looking at chlorogenic acid, which is one of the polyphenolic compounds we're looking at. We're looking at 3 in total. We made 5 solutions of known concentration from a standard, and those will be used to create a calibration curve. And so for the calibration curve, what we do is we run these standard concentrations through our HPLC and it will come up with something like this here. We get 2 peaks. This peak here is our solvent, and it comes through first because it has no affinity for the stationary phase. Our second peak, which we see here, is going to be, for our standards, is the chlorogenic acid. And we can integrate these peaks to find an area. And if we plot these areas against the concentration we know, we get a calibration curve. And notice this is a straight line. That's because the peak area is proportional directly to the concentration that we have. We used 1,000, 800, 400, 200, and 100 micrograms per milliliter. So if we come back, we will then run our potato extracts using an identical method, so that way we can tell that the peak coming off is actually the chlorogenic acid. We chose a 25-minute runtime because the chlorogenic acid does have a retention time of about 22.5 minutes. And so, working, like Dr. Beaton said earlier, this project unfortunately has progressed much more slowly than we had anticipated, so there's still a lot of work to be done. The calibration curve has been started but not yet finished, so we have to finish those, particularly for the chlorogenic acid. And then we can run our potato extracts and see how much chlorogenic acid we have actually present, and see what kind of variation there is between the potatoes we tried. Again, we tried the red potato, a yellow potato, and a purple potato. And after that, I won't be doing this part, but Diganta and his people he's working with will continue on and look at the inhibitory activity of these polyphenolic compounds that we've collected on aldose reductase. Aldose reductase is one of the enzymes responsible for the formation of cataracts. And so if we manage to inhibit this, it can help to significantly reduce the amount of the prevalence, I guess, of the cataracts we see, hopefully worldwide. That would be the intention. So I would like to thank Dr. Diganta Kalita, the postdoc I've been working with, for allowing me to help him. It's been a good experience. I've enjoyed myself a lot. And Dr. Sastry Gianchi of the San Luis Valley Research Center for Colorado State University. He's the head doctor working with Diganta on the project. And then I would like to thank Dr. Beaton, Dr. Renee Beaton, and Dr. Chris Adams, who have kept me from getting completely lost on my first time out on actual research. It's been fun.